Let us talk now about the test on the quadratic form of misclosures and of residuals. Here we are again in the table summarizing these tests, and we have the two tests: quadratic form of misclosures, quadratic form of residuals. And of course, we know that the mean value, the expected, the population value of misclosures and residuals is 0. Okay, that's the expected value. Anything different will indicate that there is a bias in the computed residuals. The situation as far as the variance goes, again, we're not really looking at the variance, but the variance factor, this scale factor. The a-priori variance factor may be known. The a-priori variance factor may be not known, so we use the a-posteriori variance factor. This is for the test, for the quadratic test, the test of the quadratic form of the misclosures. Null hypothesis: the misclosures they follow a normal distribution with 0 mean and a variance that is the variance of its covariance matrix. And again, this W prime is a special type of misclosure that we discussed in 2 video lectures ago. The statistic Y, this is quadratic form, so here we have, this is the quadratic form of misclosures. Okay, W prime transpose multiplying by the weight matrix, presented here as the covariance matrix of the misclosures inverse, multiplying the vector W prime. If we are in the case that we don't know the a-priori variance factor, we are using the scaled covariance matrix of the misclosures. The PDF, if we know the a-priori variance factor, we use a chi-square distribution with an argument m prime. And what is m prime? M prime is the number of misclosures in the subset. So again, we are dealing with a test that fits very well with the conditional case of adjustment. In the situation where we don't know the a-priori variance factor, we use the a-posteriori variance factor. This is the PDF. We use the Fisher distribution, is scaled by m prime, which we already defined, and the arguments of the Fisher distribution. Fisher distribution is a distribution that is computed based on 2 degrees of freedom. So we have the first degree of freedom here is m prime, number of misclosures in the subset, and we have ni, which is our good old friend ni as degrees of freedom, given by m minus u, and again, this is the in the conditional case, number of conditional equations minus number of unknowns. The statistic, well, just define the statistic already. This is the test. This is the test. We will be testing if the statistic y lies within a interval that is given by this quantity here and this quantity there. So this is the quantity that we draw from the chi-square distribution with m prime degrees of freedom and alpha over 2. This is the significance level, and 1 minus alpha over 2. That's the for the other part. So this is here alpha over 2, and we have all the way here, this is 1 minus alpha over 2. And now we can look at the test on the quadratic form of the misclosures. And we have the situation that the a priori variance factor is known. Yes, it has to be known, because what we are indeed testing in this test of the quadratic form of the residuals is the statistical equivalence between the a priori variance factor and the a posteriori variance factor. So we can only do this test if we know the a priori variance factor. Residuals have a normal distribution. This is the null hypothesis with zero mean, and the variance is the variance as given by the covariance matrix of the residuals. This is the statistic. Okay, the statistic is nothing else but the ratio between the a posteriori variance factor and the a priori variance factor is scaled by ni, and what is ni? Number of degrees of freedom. The probability distribution function that we're going to get is the chi-squared using ni degrees of freedom, and here we have the test. It is a two-tail test again. We have reformulated the statistical statement in such a way that we are testing the value of the a priori variance factor. If it lies between the interval, the left-hand side limit is given by this expression, and the right-hand side is given by this expression here. Okay. So now a little bit of explanation on the table. This is basically a repetition that what we already said. Test on the quadratic form of misclosures first. The null hypothesis that the misclosures have a normal PDF. We have two situations. We either know the a priori variance factor, we don't know the a priori variance factor. The basic difference in the test is, if we know, use the chi-square distribution. If you don't know, use the Fisher distribution. And the important thing here is that we'll be essentially using a scaled covariance matrix of the misclosures. This is the statistic. We either use these if we know the a priori variance factor. We use this statistic here if we don't know the a priori variance factor. Now let's talk about a more common test that is done. I would say is heavily done. And it is a test that tells us a lot. The test on the quadratic form of the misclosures, also known as the chi-square test of the variance factor, chi-square test of the variance factor, or also known as global test. So the test, the null hypothesis is that the a priori variance factor equals to the a posteriori variance factor. This is a statistical statement, as we presented already. And why we call that a quadratic form? For the misclosures, it was very clear. But for the residuals, it may not be, but it is if you look at here. So this is the a posteriori variance factor. The equation that we use to compute. This is the squared of the residuals. this is the covariance matrix of the observations, is scaled by the a priori variance factor. So we can now write the quadratic form in this way. It is going to be ni, which is here, multiplying sigma hat naught squared, that is the a priori variance factor, divided by the a posteriori variance factor. Okay, so this is basically the statistic. So this statistic is indeed the quadratic form. But what happens if this test fails? Okay, and that's something that is very intriguing, because sometimes we do the test, sometimes we compute, we do in practice, we may have the a priori variance factor equals to 1, and then we compute the a posteriori variance factor, it may be equals to, I don't know, 5 million. Okay, and say, what the heck are you doing? Okay, of course, if you test, it's going to fail. So let's look at what happens if we do the test. Again, we can only perform this test if we know the a priori variance factor, or if we consider it known. Usually we make it equals to 1. Not necessarily. You may have specifications from a past adjustment. You may have a different value for the a priori variance factor. Okay, but usually equals to 1. So we have two outcomes. We have the outcome that the test passes in the sense, or the null hypothesis is not rejected. Again, null hypothesis is that these two guys are the same. The test passes, we're happy. What does it mean? It means that the matrices are properly scaled. So not just the covariance matrix of the observations, but all the other covariance matrices that we compute, they are properly scaled. We don't need to do anything else with them. Just go and use them. And we can use the a priori variance factor in the quality control. Okay, using all these matrices that are properly scaled. So we are happy. Life is beautiful. Now, sometimes the test fails. What does it mean? It means that there is something wrong in the input. So look for reasons for the failure. Look for the reasons. Okay, we're going to look at potential causes for failure. Fix what is wrong. Rerun the adjustment. What happens now if the a priori variance factor is unknown? If it is unknown, we cannot do the test. Okay, so if a priori variance factor is unknown, we know that the weight matrix, the covariance matrix, is not scaled. So the weight matrix, as you know, would have to be scaled by this guy here, but it's not, because you don't know. Okay, so we cannot guarantee the scaling of this covariance matrix. So and that's why comes this approach of using the posteriori variance factor to scale the estimated matrices. For example, the covariance matrix of the parameters will be scaled by the a posteriori variance factor, giving them the scaled covariance matrix of the parameters. And we can do that with any other. We can do that with the residual. This is the scale covariance matrix of the residuals, which is nothing else but the scale that we got from the adjustment multiplied by the a posteriori variance factor. And in this case, we're using the a posteriori variance factor in the quality control. So that's a very nice summary of the meaning of the test and what we should do if we don't know the a priori variance factor. If the test fails, what might be wrong? So let's look at it. Presence of systematic errors in the observations. So essentially there are outliers and there are systematic effects. Have to be treated. The systematic effects have to be removed, and they might have been removed well, with a simplified equation for refraction, for example, so that it's still systematic effects that are lingering in the data sets. Departure from normality in the observations. This, of course, has to do with the presence of errors, systematic errors and blunders. We may have lots of blunders. We may still have the systematic errors. Improper assignment of variances to the observations. This basically means that our variances, the variances in our covariance matrix of the observations, they are not really good. Okay, they are, well, they're improper. Okay, they may be too large or too small. Shortcomings in the mathematical model. Yeah, that may happen, even though if we're dealing with problems that have been very established, like, well, a traverse, a triangulation, and you name it, GNSS vector adjustment, we should not expect that the mathematical model is wrong. But anyway, this is one of the causes of the failure in the test. And lastly, some bad adjustment setups. For example, we may have stations that are held fixed at wrong coordinates. So, which means that if we do the test, okay, do the test here. If it passes, we use it. If don't passes, we look at the causes. Okay. So we are only going to rescale covariance matrices if we don't know the a priori variance factor, and that means that our scale, our matrices may not have been properly scaled. Okay, so pay attention with that.